again with the second part of Pint of Science in Sweden with David Docquier. So David is a postdoctoral researcher and he is a Belgian climatologist working at the Swedish Meteorological and Hydrological Institute, SMOE, as we say in Sweden. He has done his PhD in Belgium and worked in different Belgian universities and has investigated the consequences of climate change on the ice and the sea, if I have understood correctly. He is now in Sweden, working at SMOE, also in Norrköping, as Mathieu is also working there. So please, David, let us know what you work with exactly. And please, you can begin by sharing your screen.
Hi everyone, thank you very much, Karim, and the Pint of Science Sweden team for organizing this. So I will share my screen. Okay, I cannot share my screen while the other participant is sharing, so. I think you have to stop sharing, Karim, because I cannot. Yeah. Thank you. Okay, can you see the presentation now?
Yes, we can see it. Very, very good.
Okay, so I'm David Docquier, Belgian researcher at the Swedish Meteorological and Hydrological Institute. And I work on the interactions between the ocean heat and the Arctic sea ice. So please don't hesitate to interrupt me if you have any questions during the presentation, and I'm pleased to answer them. So I will see four main points during my presentation. Sea ice in the current context of climate change, then the influence of the ocean on the sea ice, then I will talk about my research, and finally about the fate of Arctic sea ice. What will happen to the Arctic sea ice in the future? So first, sea ice in the context of climate change. So what is sea ice? We have here a picture on the upper left showing icebergs and sea ice. So icebergs are the big chunks of sea ice in the middle of the pictures. They are typically 10 up to 100-meter high, so they are quite high, and they break off from ice shelves. So it's basically ice coming from land. While sea ice surrounds those icebergs, so these are small flows of ice which float onto the ocean, and they are typically 2 to 3 meters high, so they are much thinner than icebergs. And the difference is that they form on the surface of the ocean when the ocean freezes in the winter. So sea ice, contrarily to land ice, does not raise sea level if melted, and you can make this simple experiment of putting an ice cube in a glass of water. So the diagram on the right side shows this. So you first put the ice cube in the water, so you raise the water level because you add your ice cube, the second picture, and then if the ice cube melts, it does not raise or lower down the level of the water because it was simply there before, it was floating on the ocean. So what is really contributing to the sea level rise is the ice coming from land, from ice sheets and from... So typically when we look at the world, we see this kind of maps where we barely see Antarctica and the Arctic. So what we do in my research is using instead these kinds of maps. So on the left side, you have a representation of the Arctic Ocean and the continent around the Arctic Ocean. So this is in the northern hemisphere, and in white you have the sea ice. And on the right side, you have Antarctica. So the Antarctic continent surrounded by the Southern Ocean. And in white, again, you have sea ice. So in both hemispheres, in the polar regions, you have sea ice.
David, that's a very interesting map. Can you just show Sweden where it is so we can have some idea where we are?
Back. So Sweden is just
there, yeah.
Right here. Yes, you have all Scandinavia here, Greenland, sorry, Siberia, and North America.
Great, thank you.
So you all probably know that the Arctic has changed a lot in the past years, especially the sea ice in the Arctic has decreased a lot. And this movie on the left side shows from year to year, from the late 70s up to now, so that's about 40 years of satellite observations, the sea ice concentration in the Arctic, and you see it from March at the top, and for September at the bottom. So in March, you are at the end of the winter, you have more sea ice, and in September, end of summer, you have the minimum of sea ice. But in both periods, you see that overall, you have a decrease of sea ice over the years. And if we summarize this by the total Arctic sea ice area, so really the total area of ocean that is covered by sea ice in the Arctic, we end up with this plot. So this is the evolution of sea ice area in the Arctic over time, from the late 70s to now. In blue, you have March, and in red, you have September. And you see for both periods a decrease in sea ice, which is more pronounced in September. So we start with 6 million square kilometers in the late 70s, and we end up with about 4 million square kilometers now. So what are the causes of those changes in sea ice? First, we have the external forcing. So this is the ensemble of external factors, either human or natural, that cause sea ice changes. And one of the most important factors is the anthropogenic global warming, which is caused, for example, by emissions from cars and from industry. So all the carbon that is going into the atmosphere enhances the greenhouse gas concentration in the atmosphere, which raises the global temperature, which melts the sea ice in the end. A second factor that causes sea ice changes is the internal variability. So the climate is very chaotic, and there is variability that is internal to the system itself. And a way to compute this, so it's not very well understood, and it's a quite complicated concept, but a way to understand it is to run the same model with exactly the same parameters and the same external forcing, but with slightly different initial conditions. So for example, you change a bit the sea surface temperature of the model, and you see how the model reacts to this. And this diagram here shows the same model that was run 40 different times, and you end up with 40 different curves for the sea ice extent over time. So that gives you an idea of the uncertainty that is linked to the internal variability. A third cause is the positive feedbacks. So for example, you have the ice albedo feedback, which is represented on this diagram. So the ice reflects a lot of solar radiation. And if we melt this sea ice, what is happening now, we have more ocean. The ocean absorbs the solar radiation more than sea ice, and it increases the temperature, which gives more melting of the sea ice. So this is a positive feedback. You have also atmospheric processes, and this is a picture of a big storm that occurred in the Arctic Ocean in 2012, and it resulted in a massive loss of sea ice during the summer of 2012. And the last one is oceanic processes. So you have a broad range of oceanic processes that operate, and I focus especially on those processes. And these two, atmospheric and oceanic processes, they are either associated with anthropogenic global warming or internal variability. So this is for the sea ice in climate change context. Now we'll have a deeper look at the ocean influence on Arctic sea ice. So this map here shows the Arctic Ocean, so centered on the North Pole. And in red, you have the warm ocean currents. In blue, you have the cold currents. And you have the biggest input to the Arctic is the Atlantic water inflow. And you have two main branches via the Barents Sea. So north of Sweden and Norway, you have the Barents Sea. And one of the branches from the Atlantic water comes here. And the other one goes through the Franz Strait in the middle of between Svalbard and Greenland. So you have two main pathways, and this warm water will melt a substantial amount of sea ice in the end. So it's very important to monitor accurately those ocean currents. So those diagrams, they show, in fact, the ocean view. So we are in the ocean. You have depth here on the y-axis. So it's the first 250 meters of ocean depth. And on the right side, you are in the Atlantic. On the left side, in the central Arctic. So you have this Atlantic water, this AW at the bottom, which is the warm water in red that goes from the Atlantic to the Arctic. And on top of the Atlantic water, you have a colder, fresher water because you have it's colder because you have the cold atmosphere on top of it, and you have the formation of sea ice here, the small flows of sea ice. And this was the image of the early 2000s. But now, in the mid-2010, we had a big change in the last year, and we have a bigger inflow of the Atlantic water. So you have the arrows that are growing, which means that the Atlantic water, the flow and the heat from the Atlantic water are increasing over the years. So you have more heat coming into the Arctic, and you have an enhancement of the upward fluxes from the ocean, which melts the different flows of sea ice here, especially in the Barents and Kara Sea.
David?
Yes.
Do you know why we have this inflow from Atlantic? That is.
Yeah, so it mainly comes from the Atlantic. The Atlantic it's not only the temperature of the ocean that is increasing, but also the flow. So we have noticed that the flow of the North Atlantic also increased in the past years.
But
so
we don't know why.
So for the temperature, it's probably linked. We don't know exactly, but for the temperature, it's probably linked to the global warming, partly. And for the flow, it's internal variability, but we are not sure at the moment what are the exact causes behind those processes, because it's quite recent, in fact.
Okay, thank you.
So now if we're going to have a look at my research in more detail. So this picture shows my team with nice, so I'm surrounded by nice people at SMHI, and this is the team of Rosby Center, so the climate group at SMHI. My supervisor is Torben König, and here I show you the main tool that we use at work, so computer, so not only a laptop, but also a lot of computers. So these are servers. So we run, as Mathieu explained before, we also use a lot of computers to make our simulations. And we use the EC-Earth model. So this is a global climate model which encompasses the different components of the climate. So which are the atmosphere, the ocean with sea ice on top of it, the land, and sometimes ice sheets. So there are a lot of different processes between all these components that are represented in the climate model. And my research is embedded within the OCIS project, so the two-way interactions between ocean heat transport and Arctic sea ice. So what is a climate model? This diagram on the upper left shows the representation of the Earth divided into different grid cells. That is how a climate model sees the world. And in each grid cell, we compute the equations of physics. You have them here below. So you have a set of the equations that are computed at each grid cell. I don't expect that you understand all of them, but it gives you an idea how the model behaves. So you have to resolve this in each grid cell to try to find what is the pressure, the temperature, the velocity, etc. On the bottom right here shows how you translate those equations of the physics into the computer, so in programming. So we put all these equations in the computer, and we have, for example, this bit of code which is used in a model. And on the upper right, we have a representation of Europe with different grid cells. So you see that in the 1990s, we had quite coarse models with a very large size for the different grid cells, about 500 kilometers size for each grid cell. While in the end of the 2000s, we reach much finer grid size. So we have a much better accuracy of the different processes occurring in the climate. So finer grid size, it means that we have a better representation of the world with the climate models now. So the central question of my research is, how does the transport of heat by the ocean affect the Arctic sea ice? So here for example, we can do a control simulation where we represent the present day climate. Then we have run a set of sensitivity experiments where we increased the ocean heat transport, and we compared those two sets of experiments, a control simulation with a sensitivity experiment. And we end up with this kind of plot where we see the change in Arctic sea ice area with a change in ocean heat transport. So you see with this plot that when you increase the ocean heat transport coming into the Arctic, then you decrease strongly the Arctic sea ice area. And so each dot in this plot shows one different experiment. So in terms of the destiny of Arctic sea ice, what will happen to the sea ice in the future, we can analyze this from observations. So if we extrapolate observational data, we end up with this kind of diagram. So this is a nice representation, outreach presentation showing the different levels of warming on the x-axis, and on the y-axis you have the different month of the year. So let's take September, which is the minimum Arctic sea ice. Minimum Arctic sea ice area. So we are now today a bit more than 1 degree above the pre-industrial level. And if we extrapolate the observations, we see that in September, we have ice-free conditions in the Arctic a bit above 1.5 degrees. So you have to know that ice-free, we define it usually by less than 1 million square kilometers, because you still have some remaining ice in the Canadian archipelago, but not much sea ice. And if we take the 2-degree warming level, for example, then we see that we have ice-free conditions between approximately July and October. So this is based on observations. But there is, of course, a large uncertainty also that is linked to the way observations are done. That's why usually we use different sets of observations. And now, based on climate models, this is first the historical period, and this is again the evolution of Arctic sea ice area from the 1950s to now. So in thick black, you see the thick solid black curve is the observations. And all the other colored curves are the different models. And you have here 47 models, so the latest global climate model. So this is a lot of models, but you see that the spread is very high. You have a very large spread in the models, which means that you have a big uncertainty. But if you compute the mean of all models, you end up with the dashed black curve, and you see that it's not so bad compared to observations. And for September, it's even better. You have a good match between the multimodal mean and the observations. Now, if we look at, so those models can simulate the future. If you let them run using different scenario, then you can use optimistic or pessimistic scenario. This is the result from an optimistic scenario. So until the end of this century, for March in the top and for September in the bottom, again, Arctic sea ice area. You see that in March, there is not much variation. You have a small decrease, but it's not much. And in September, you have a more pronounced decrease. It's not so big, but you have a decrease of about 2 million square kilometers by the end of the century in average. But again, the spread in the models is very high, meaning that you have a model uncertainty linked to that. And now, if we look at the pessimistic scenario, where we increase a lot our carbon emissions compared to now, then we, of course, have a decrease in sea ice area in March and September, which is quite large. And if we look at September, we start at 4 million square kilometers and we reach ice-free state around 2060, so less than 1 million square kilometers. And you see that by the end of the century, you have almost no sea ice. So it really depends, the fate of sea ice really depends on the scenario that you follow. So in conclusions, we know that climate is changing, the Arctic is warming and losing sea ice, and the future will highly depend on the scenario that we will follow. So I think we really need to start reducing, to continue reducing our carbon emissions, to take care of our environment, and also to adapt to climate change. So the exact processes behind are very complicated, we have seen. So the ocean has a strong influence on the sea ice. And again, as in all research, more research is needed to really understand what is happening. Because you have seen this large spread in models, so there is something wrong and something good with the models, but we need to continue our research to find out what are the good and the bad things. And if you want to get more information about my research, you can have a look at my website. And if you have questions, I'm happy to answer either now or by email.
Thank you very much, David. I will stop sharing live now, and I will also stop the record. Then we can have informal discussion now. So thank you very much. Okay, the recording has stopped. So there is already question online. So can you see this question, David?
I'm trying to see
on the chat. Can you read this question? Oh, I can read that for you if you want. So why is sea ice much more decreased in September compared to March? And March seems not much changes during the time until now. So is the winter always sufficient to produce the same ice as the year before?
Yeah, good question. So first, September, why September compared to March? So if we go back to this slide.
Yeah, that one.
Yeah. Yeah. Okay. I cannot enlarge it again, but I don't know why.
I think each participant can zoom on what they want on your slide. If you go to view option on the top and then zoom ratio, you can zoom on your slide. Yeah.
Yeah. Okay. I don't have access anymore. I don't know why. But in September, you have a more positive, I would say, more positive feedback back to that act. So in both periods, you have a combination of positive and negative feedbacks. And in September, the ice albedo feedback acts strongly because you have a huge loss of, you have melting of sea ice. So as I explained, you have more absorption by the ocean compared to the sea ice. So this ice albedo feedback is much more enhanced, in fact, in the summer compared to the winter. You have more melting in the summer, and that leads to this higher melt in September compared to March. Now, so is the winter always sufficient to produce the same ice as the year before? No. If you look at this plot, you see that even in March, you have a decrease in the sea ice area in the Arctic. So even in March, partly due to the rising temperature of the atmosphere, but also from the ocean. So we have seen that the ocean has a strong influence on the sea ice, and you have for example, one of the seas in the Arctic, the Barents Sea, is very much affected by the amount of heat from the ocean, and we have seen a strong reduction in the sea ice cover in the Barents Sea in the last years. So I don't know if I answered the question.
I think so. Yes.
Yeah. And I have another question from Mathieu. Is there a need for a finer grid to improve the model, or the current resolution is enough? Good question. So there are different schools in climate trying to use always use a global climate model to simulate the whole system, but with a coarse resolution. But because of course, if you run a global climate model, you need a lot of computing resources. So the other school is to use less expensive regional climate model, I would say, but running at finer resolution. So there are different approaches. The advantage of using a global climate model is that you really simulate the whole system and you take into account all processes. But yes, of course, using a finer resolution is always better, and we have seen in our studies that if you use a finer resolution, you really represent the ocean currents in a better way. So by representing those by better representing those ocean currents, you better represent the sea ice area. So it makes a difference, but of course you have to have a trade-off between the computer resources and the processes that you represent in a system. And the second question is not directly connected to your talk. What would be your best argument to convince a climate change denier? From what? Could you precise, Mathieu?
Mathieu, you can talk, I think.
Yeah, well, I mean, since you're working with climate and we see all around people denying climate change, and so since you are working with it, what would you tell a person denying that there is a change of climate and this is just